Look up on a clear night and the sky appears full. Thousands of stars, the pale river of the Milky Way, the faint smudge of a galaxy 2.5 million light years away. It looks like the universe is crowded. It is not. What you are seeing is a lie, told by light. The overwhelming majority of reality is not made of stars, or planets, or gas, or dust. It is made of distance. Between every object you can see, there is an emptiness so vast that if you placed every atom in the visible universe side by side, the matter would not fill a fraction of 1% of the space it inhabits. Tonight, we're going to show you how empty the universe actually is. And once you understand the scale, you will never look at the night sky the same way again. If this kind of deep science is what you come here for, go ahead and hit like and subscribe. It genuinely helps us keep making these, and we have a lot more coming. Are you comfortable? Let's begin. Go outside tonight. Find a place away from the street lights, away from the glow of buildings and parking lots and highways. Let your eyes adjust, give it 20 minutes, and then look up. What you will see is one of the most beautiful and most misleading images a human being can experience. Stars, thousands of them, faint ones, bright ones, blue ones, reddish ones. The pale, milky band of our galaxy stretching from one horizon to the other, like a river of light frozen mid-current. If you are in the southern hemisphere, you can see the Magellanic Clouds, two companion galaxies hovering like detached pieces of the Milky Way. If you're in the north, you might catch the faint smear of Andromeda, a spiral galaxy 2.5 million light years away, visible to the naked eye as a tiny blur of light, no bigger than a thumbprint held at arm's length. It looks full. It looks populated. It looks like the universe is a crowded place, dense with structure and light and matter. Every human civilization that has ever looked at this sky came to the same intuitive conclusion. The heavens are abundant. The cosmos is rich. The space above us is filled with things. And that conclusion has ancient roots. It is not a modern misunderstanding. It is one of the oldest ideas in human history, and every major civilization built its cosmology around it. The ancient Greeks imagined the universe as a set of nested crystal spheres, each one carrying a planet or the stars, stacked tightly around the Earth like layers of an onion. The outermost sphere carried the fixed stars, and beyond it there was nothing, or perhaps the realm of the divine. But the point was that the cosmos was compact. Everything was close. Everything was contained. The distance from the Earth to the outermost sphere was finite and, by the standards of what we now know, laughably small. Aristotle's universe could have fit inside the orbit of Saturn with room to spare. The Egyptians imagined the sky as a goddess, Nut, arching her body over the Earth, her skin decorated with stars. The Mesopotamians saw a solid dome holding back a celestial ocean. The Norse imagined sparks embedded in the skull of a giant. In every case, the cosmos was small, close, populated, and personal. The sky was not an abyss, it was a roof. Even after the Copernican revolution displaced the Earth from the center of the cosmos, the assumption of a compact and densely populated universe persisted for centuries. Copernicus moved the sun to the center but did not dramatically expand the size of the universe. Kepler imagined the planets nestled inside geometric solids, stacked neatly around the sun. It was not until the 20th century when Edwin Hubble demonstrated that the fuzzy nebulae visible through large telescopes were in fact entire galaxies millions of light years away, that the true scale of the cosmos began to emerge. And even then, The emotional adjustment lagged behind the science by generations. It still lags today. The cultural inheritance of a small, full, nearby cosmos is embedded in how humans process the night sky. It is not just a visual illusion. It is a psychological one, reinforced by thousands of years of mythology, religion, art, and storytelling that all assume the same thing. The universe is crowded, and we are in the middle of it. That assumption survived longer than it should have because of another, more subtle trick. The way we build images of the cosmos reinforces the illusion, even when the science behind those images tells the opposite story. Consider how a typical astronomy photograph is made. A telescope points at a region of the sky and opens its detector for hours, sometimes days, collecting every photon that arrives from that direction. The resulting raw data is not a photograph in any normal sense. It is a collection of signal counts at different wavelengths, most of which are invisible to the human eye. Infrared light is assigned a visible color. Ultraviolet light is assigned another. Contrast is stretched. Brightness is compressed. The final image is not what the sky looks like. It is a translation, a carefully constructed visualization designed to reveal structure. And that design choice has a consequence. Every astronomy image ever published is optimized to show you what is there. No image is optimized to show you what is not there. The black background of a Hubble photograph is not presented as the subject. It is treated as the absence of a subject. Your eye slides past it and lands on the galaxies, the stars, the glowing clouds. The emptiness between them is treated as dead space, as margins, as the part of the image that does not matter. But the emptiness is almost everything. In a typical deep field image, the luminous objects, the galaxies and stars and gas clouds, occupy a vanishingly small fraction of the actual volume of space being depicted. The rest, the overwhelming majority, is the black background that your eye is trained to ignore. If the image were redesigned to represent volume faithfully, with each pixel's brightness proportional to the average density of matter along that line of sight, nearly the entire frame would be pure black. The galaxies would be invisible specks, too small and too faint to register against the dominant emptiness surrounding them. We do not make images like that because they would be boring. They would show almost nothing. But almost nothing is what the universe mostly is. The images we prefer are the ones that lie to us in exactly the way we want to be lied to. They show us the exceptions and hide the rule. That conclusion is wrong. It is not slightly wrong. It is catastrophically, overwhelmingly, almost comically wrong. And the scale of how wrong it is will be the subject of everything you are about to hear. The night sky is lying to you, not with malice, not with intent, but with a bias so deep and so fundamental that it distorts every intuition you have ever formed about the universe. The bias is this: you can only see the things that shine. That sounds obvious. Of course, you can only see things that produce or reflect light. But the implication of that simple fact is enormous. Because the universe is not organized around the things that shine. It's organized around the things that do not. The spaces between the stars are not gaps in an otherwise crowded room. They are the room. The stars are specks of dust on the floor of a cathedral so vast that the dust is functionally invisible against the scale of the emptiness that holds it. You are looking at the dust and concluding the cathedral is full. This is the first and most important thing to understand about cosmic emptiness. It is not a detail. It is not a footnote. It is the dominant condition of reality. And everything you see when you look at the sky, every point of light, every galaxy, every nebula, every cluster, exists as a tiny exception to a rule that governs almost everything else. The rule is absence. The rule is distance. The rule is that almost nothing is anywhere. And the places where something exists are so rare and so small and so far apart that the emptiness surrounding them is not the background. It is the main event. We're going to build this understanding one scale at a time. And we're going to start in the most familiar place we know, the solar system. You live on a planet that orbits a star. Around that same star orbit, 7 other major planets, 5 officially recognized dwarf planets, hundreds of moons, millions of asteroids, and billions of comets. It sounds busy. It sounds like a system teeming with objects and activity and structure. And if you have ever seen a diagram of the solar system in a textbook or on a classroom wall, that is exactly the impression it gives. 8 planets, neatly spaced, orbiting a bright yellow star in the center. Everything looks close. Everything looks organized. Everything looks compact. Those diagrams are amongst the most misleading images in all of science education. They have to be misleading, because if they were drawn to scale, you would not be able to see the planets at all. The distances between the objects in our solar system are so large relative to the objects themselves that any honest attempt to depict the system on a single page would reduce every planet to an invisible dot surrounded by blank space, stretching in every direction. Let us start with something familiar. The moon is the closest major object to Earth. You can see it almost every night. It looks close. It feels close. It is not close. The moon orbits at an average distance of roughly 240,000 miles from Earth. That is far enough to fit approximately 30 Earths side by side between here and there. If you could drive a car to the moon at highway speed without stopping, the trip would take roughly 5 months. Now look at the sun. The sun is roughly 93 million miles away. That is nearly 400 times the distance to the moon. Light, which travels at roughly 186,000 miles per second, takes about 8 minutes to cover the gap between the sun and the Earth. When you see the sun in the sky, you are seeing it as it was 8 minutes ago. If it vanished right now, you would not know for almost 10 minutes. These numbers are large, but they're still comprehensible. The human mind can stretch to imagine 93 million miles, even if it cannot truly feel the distance. The problem begins when you move outward. Mars, our closest planetary neighbor in the outward direction, orbits at a distance that varies between roughly 34 million and 250 million miles from Earth, depending on where both planets are in their orbits. When Mars is at its closest, a radio signal sent from Earth takes roughly 3 minutes to arrive. When it is at its farthest, that signal takes over 20 minutes. Every rover we have ever sent to Mars operates with that delay built into every command. Jupiter orbits roughly 484 million miles from the Sun on average. Saturn sits at roughly 886 million miles. Uranus at roughly 1.8 billion miles. And Neptune, the outermost major planet, orbits at an average distance of roughly 2.8 billion miles from the Sun. 2.8 billion miles. Light takes over 4 hours to travel from the Sun to Neptune. A spacecraft traveling at the speed of the Voyager probes, the fastest objects humanity has ever sent into deep space, would still need over 12 years to cover the distance. And Neptune is not even the edge of the solar system. And here is the detail that most diagrams never communicate. Between all of these planets, there is effectively nothing. Not nothing in the philosophical sense, nothing in the physical, measurable, scientific sense. The space between Mars and Jupiter is not filled with gas or debris or structure. It contains the asteroid belt, yes, but the asteroid belt itself is overwhelmingly empty. If you placed every asteroid in the belt together into a single object, it would be smaller than our moon. The average distance between individual asteroids in the belt is roughly 600,000 miles. You could fly through the entire asteroid belt in a straight line, and the odds of hitting anything are astronomically small. The belt that looks so dense and dangerous in science fiction movies is, in reality, a vast expanse of vacuum with a few scattered rocks drifting through it. This is the solar system. This is the place we call home. And it is almost entirely empty. To understand how empty, consider a scale model. Shrink the sun down to the size of a basketball. A standard basketball, roughly 9.5 inches across, sitting on a sidewalk somewhere. At that scale, the Earth would be a small bead, roughly 2 millimeters in diameter, smaller than a peppercorn, and it would be sitting 86 feet away from the basketball. Not 86 inches, 86 feet. That is nearly the length of a basketball court. Mars, at the same scale, would be an even smaller bead, roughly 130 feet from the basketball. Jupiter, the largest planet, would be about the size of a cherry, and it would be sitting roughly 440 feet away, nearly 5 football fields from the basketball. Saturn would be slightly smaller than the cherry, roughly 800 feet from the basketball, and Neptune, the outermost major planet, would be a blueberry sitting nearly half a mile from the basketball on the sidewalk. Half a mile. From a basketball to a blueberry. Everything between them. Air. Empty space. Nothing you could see, touch, or detect with any instrument short of a telescope specifically designed to find tiny objects at enormous distances. And we have not even left the solar system yet. Beyond Neptune, there is Pluto, roughly 3.7 billion miles from the Sun on average. In the scale model, it would be a grain of fine sand, sitting roughly 2/3 of a mile from the basketball. And beyond Pluto, there is the Kuiper Belt, a region of icy objects stretching outward into a zone that thins and fades into the most remote frontier of our solar neighborhood. Beyond the Kuiper Belt, at distances so great they strain any metaphor, there is the theorized Oort cloud. The Oort cloud is a hypothetical shell of icy objects surrounding the solar system at distances up to roughly 1 to 2 light years from the Sun. No spacecraft has ever come close to reaching it. No telescope has directly imaged it. Its existence is inferred from the behavior of long-period comets that fall inward toward the Sun from extreme distances and extreme angles, suggesting a vast spherical reservoir of frozen material enclosing the entire system like a shell. In the scale model, if the Sun is a basketball on a sidewalk, the inner edge of the Oort cloud would be roughly 30 miles away. The outer edge could be as far as 1,600 miles, roughly the distance from New York to Denver, and the nearest star, Proxima Centauri, would be another basketball sitting over 4,000 miles from the first. Farther than New York is from Rome. And across those 4,000 miles, one cherry, a few beads, a handful of grains of sand scattered across the first half mile of sidewalk, then 1,600 miles of nothing before you leave the Sun's domain, then thousands of miles more of nothing before you reach the next point of light. That is the solar system and its nearest neighbor. A few specks of matter separated by the width of a continent. There is a way to feel this emptiness rather than just calculate it. In 2014, a designer named Josh Worth built an interactive webpage called If the Moon Were Only One Pixel. It is exactly what the title describes. A 2-scale map of the solar system in which the moon is rendered as a single pixel on your screen. Everything else is sized and spaced accordingly. The sun, at that scale, is a small circle. The planets are dots, some of them barely visible, and between them is the real subject of the page: nothing. Scrolling. If you visit the page and begin scrolling from the sun toward Mercury, the first thing you notice is how long it takes. You scroll and scroll, and the screen is blank. A pale, empty strip of space with nothing in it. No markers, no waypoints, just distance, represented honestly. When Mercury finally appears, it is a speck so small you might miss it if you were not watching carefully. You scroll onward, more nothing. Venus arrives, then Earth, each one preceded by a long, featureless stretch of empty screen that makes the previous gap feel short. By the time you reach Mars, the experience has shifted from curiosity to something closer to discomfort. The emptiness is not dramatic, it is boring, it is tedious. It is a flat, unbroken expanse of nothing that goes on so long your thumb gets tired on the scroll wheel. And that tedium is the point. The solar system is not exciting between objects. It's empty between objects. Relentlessly, monotonously, aggressively empty. The spaces between the planets are not dramatic voids filled with cosmic wonder. They are blank. They are featureless. They contain nothing worth looking at because there is nothing there to look at. The journey from Mars to Jupiter is where most people give up. The gap is enormous. At the page's scale, it takes minutes of continuous scrolling to cross. The asteroid belt passes somewhere in the middle, but at this scale, the asteroids are too small to render. They do not even appear. The belt that science fiction depicts as a dense, dangerous obstacle course is, at an honest scale, invisible. You scroll through it without knowing it was there. Jupiter, when it finally arrives, is the first object that feels substantial. A dot large enough to notice. But the relief is brief because beyond Jupiter the distances grow even longer. Saturn is further from Jupiter than Jupiter is from the Sun. Uranus is further still. And Neptune, when you finally reach it after what feels like an unreasonable amount of scrolling, sits at the edge of a map that has communicated one thing more effectively than any textbook or lecture or documentary ever has. The solar system is not a collection of planets. It is a collection of distances, with planets as punctuation marks so small and so widely spaced that the distances are the only thing that registers. Worth included a line of text partway through the empty scrolling that captures it perfectly. He wrote that most space is just space. He was right. And the solar system is the smallest example of that truth. That is not a crowded system. That is not a full system. That is a system built almost entirely from nothing, where the matter that exists is so sparse and so tiny relative to the space it inhabits that the word empty does not begin to capture it. And here is the part that most people do not process, even when they hear the numbers. The solar system is not an unusually empty part of the universe. It is one of the densest. Compared to what lies between the stars, compared to what lies between the galaxies, compared to the vast cosmic voids that make up the majority of the observable universe, our solar system is practically crowded. It is a bustling metropolitan center by the standards of the cosmos, a place where matter is, relatively speaking, abundant, which means everything you just imagined, The basketball and the blueberry 1.5 miles apart, the grain of sand 2 miles away, the empty model stretching from New York to Tokyo with almost nothing in it. That is the least empty this story gets. We need to talk about why the sky still looks full despite all of this. Because the answer reveals something deeper about how humans perceive reality. Your eyes are not scientific instruments. They are biological tools evolved to detect light in a narrow band of the electromagnetic spectrum, tuned to the specific conditions of a small planet in a quiet corner of a single galaxy. When you look at the sky, you are not conducting a survey. You are experiencing a sensory event shaped by millions of years of evolution that had nothing to do with understanding cosmic structure. Your visual system was built to spot predators in tall grass and ripe fruit on branches. It was not built to intuitively grasp the three-dimensional distribution of matter across billions of light years. When you see a star, your brain registers a point of light. It does not register the trillions of miles of vacuum between you and that star. It does not register the trillions of miles of vacuum between that star and the next one. It sees the dots. It connects the dots. It fills the space between them with an assumption of continuity that has no basis in physical reality. This is called luminosity bias, and it affects not just casual stargazers, but professional astronomers as well. Every image you have ever seen of a nebula, a galaxy, a star cluster, or a deep field photograph was taken by an instrument designed to collect light. The instrument sees what shines. It does not see what does not shine. And what does not shine is almost everything. Consider the most famous deep space image ever taken, the Hubble Ultra Deep Field. In 2003, astronomers pointed the Hubble Space Telescope at an apparently empty patch of sky near the constellation Fornax. They held the shutter open for days, collecting every photon that arrived from that tiny window. The result was an image filled with roughly 10,000 galaxies, each one a vast collection of billions of stars spread across millions of light years. The image stunned the world. It showed that even in what looked like blank sky, the universe was filled with structure. People looked at it and said the universe is full. But that interpretation, while emotionally powerful, misses the point entirely. What the Hubble Ultra Deep Field actually showed is that even when you collect every scrap of light from a tiny piece of sky over the course of many days, the objects you find are still separated by unimaginable distances. Each galaxy in that image is millions or billions of light years from its neighbors. The space between them is not shown in the image because it contains nothing to photograph. The image looks full because it was designed to show you what is there. It was not designed to show you what is not there. And what is not there is almost everything. Every astronomy photograph you have ever seen suffers from this same distortion. Nebulae look like dense clouds of gas and dust, but a typical glowing nebula in our galaxy contains only a few thousand particles per cubic centimeter. That is still trillions upon trillions of times less dense than the air around you. The gas in a visible nebula is unimaginably thin. It only looks dense because you're seeing it across light years of depth. And even a vanishingly thin gas will produce a visible glow if you stack enough of it along a single line of sight. Galaxies look like solid pinwheels of light, but the stars within them are separated by light years of empty space. If you picked a random cubic light year inside the Milky Way, the overwhelming likelihood is that it would contain no star at all. The light of billions of distant suns merges at a distance, creating the illusion of density. But the density is the illusion. The galaxy is a swarm of separated points that only looks continuous because your eyes cannot resolve the gaps between them. The universe is full of structure that looks dense and is not. The fullness is an artifact of how light travels, how images are made, and how human eyes and brains interpret visual information. Remove the bias, remove the luminosity trick, remove the photographic compression, and what remains is a cosmos that is almost entirely empty at every scale you examine. This is the first critical insight. The universe is not full. It has never been full. The appearance of fullness is an illusion generated by the interaction between light and human perception. And once you understand that the illusion is an illusion, you can begin to see what the universe actually looks like. It looks empty, not slightly empty, not mostly empty, overwhelmingly, structurally, definitionally empty. The matter that exists in it, the stars, the planets, the gas, the dust, all of it together constitutes a vanishingly small fraction of the total volume of space. The rest is vacuum. Near perfect, near total, near infinite vacuum stretching in every direction for distances that the human mind was never evolved to comprehend. And the solar system, the place where you live, the place where everything you have ever known or loved or touched exists, is one of the densest parts of that vacuum. It is a place where matter is concentrated by cosmic standards. It is the busy intersection, the crowded marketplace, the packed stadium of the universe, and it is still, by any honest accounting, almost entirely nothing. That is the first truth of cosmic emptiness. The place you call home is already a void. You just cannot see it because the things inside it shine. But the solar system is not where the real emptiness begins. That starts when you leave, because the distance between our sun and the nearest star is not just large. It is a gap so vast that it redefines what the word distance means. And what fills that gap is something worse than darkness. It is an absence so complete that it challenges the idea that the universe was built for anything to cross it at all. The Voyager 1 spacecraft was launched on September 5th, 1977. It carried a golden record etched with sounds and images from Earth, a message in a bottle thrown into the deepest ocean imaginable. It flew past Jupiter. It flew past Saturn. It took photographs that changed how humanity understood both planets. And then it kept going. Outward. Away from the sun. Away from every planet. Into the space between stars. Voyager 1 is the most distant human-made object in existence. As of now, it is roughly 15 billion miles from Earth. It has been traveling for nearly 50 years. It moves at roughly 38,000 miles per hour. And in all that time, across all that distance, it has not come close to reaching another star. It is not even close to being close. The nearest star to our sun is Proxima Centauri, a small red dwarf roughly 4.25 light years away. A light year is the distance light travels in 1 year, roughly 5.88 trillion miles. 4.25 light years is therefore roughly 25 trillion miles. At Voyager 1's current speed, it would take approximately 73,000 years to reach Proxima Centauri if it were heading in that direction. It is not. It is heading toward a different part of the sky. But even if its trajectory were corrected, the journey would take longer than recorded human civilization has existed. 73,000 years. That number needs a moment. 73,000 years ago, anatomically modern humans were painting on cave walls and chipping stone tools in Africa and Europe. The entire history of agriculture, cities, Writing, mathematics, science, industry, and spaceflight fits inside the last 10,000 years. It would take 7 times that span to reach the single nearest star at the fastest speed any human object has ever achieved. That is the distance to the closest one. And there are an estimated 200 to 400 billion more in this galaxy alone. And we know what that crossing feels like, at least in the rough terms that instruments can report, because Voyager 1 already made part of the journey. On August 25th, 2012, Voyager 1 crossed a boundary that no human object had ever reached. It passed through the heliopause, the point where the solar wind, the stream of charged particles flowing outward from the sun, is no longer strong enough to push back against the pressure of the interstellar medium. Beyond that boundary, the spacecraft was no longer inside the sun's protective bubble. It was, by the formal definition used by NASA and the space physics community, in interstellar space. The crossing was not dramatic. There was no wall, no visible boundary, no sudden change in the view from the spacecraft's cameras, which had been powered down decades earlier to save energy. What changed was the data. The plasma instruments detected a sharp increase in the density of charged particles around the spacecraft, from roughly 0.002 particles per cubic centimeter inside the heliosphere to roughly 0.05 particles per cubic centimeter outside it. The cosmic ray detectors registered a jump in the flux of high-energy particles originating from beyond the solar system, particles that the solar wind had previously deflected. Those numbers are worth pausing on. 0.05 particles per cubic centimeter. That is the density of the space Voyager 1 entered after nearly 35 years of flight. It is not the average density of the interstellar medium. It is the density of the local interstellar cloud, a relatively dense patch of gas that the solar system is currently passing through. The broader interstellar medium between the spiral arms is even thinner. Voyager 1 crossed into what counts, by interstellar standards, as a crowded region. And that crowded region contains 1 particle for every 20 cubic centimeters. The instruments also measured the magnetic field of the interstellar medium for the first time. It was real and detectable, roughly 4 to 5 microgauss, more than 100,000 times weaker than the magnetic field at Earth's surface. Faint, present, but so weak that it would have no measurable effect on any physical object passing through it. Beyond the data, what Voyager 1's crossing reveals most powerfully is the sensory reality of interstellar space. If you could somehow stand where Voyager is now, roughly 15 billion miles from the sun, what would you experience? Darkness. Not the darkness of a cloudy night or a closed room. A darkness more complete than any environment on Earth. The sun, from Voyager's current distance, is still the brightest object in the sky, but it is no longer a disk. It's a point of light, still far brighter than any star, but reduced to a fierce pinprick, too small for the human eye to resolve into a shape. There is no planetary system visible around it. Just a single brilliant dot in an otherwise ordinary star field. In every other direction, stars. The same stars you see from Earth. In almost the same positions because Voyager has not travelled far enough for stellar parallax to noticeably change the constellations. You would recognise the sky. You would feel as if you had barely moved. And yet you would be further from home than any human object has ever been, surrounded by a vacuum more perfect than anything achievable on Earth. No sound. Sound requires a medium to travel through, and the medium here is so thin that acoustic waves cannot propagate. Even if you shouted with the force of a jet engine, the sound would not travel a single inch. The silence would be absolute, not quiet, not hushed, absolute. A silence that has persisted for billions of years and will persist for billions more. No temperature sensation in any meaningful human sense. The interstellar medium has a measurable temperature, roughly 6,000 to 10,000 degrees in the local cloud. But temperature in this context refers to the average kinetic energy of the individual particles. Those particles would strike your skin, but each one carries so little energy that the total heat transferred would be unmeasurably small. The gas is technically hotter than the surface of many stars, but it is so thin that it cannot warm anything. Temperature without density is a number without a consequence. You would not feel warm. You would radiate your own body heat into the vacuum and cool rapidly toward the background temperature of the cosmos, roughly 2.7 degrees above absolute zero. You would freeze. Not because interstellar space is cold in the way a winter night is cold, but because there is nothing out there to keep you warm. No air to insulate, no surface to reflect heat, nothing. That is what lies between the stars. That is the environment that fills the trillions of miles separating every sun from its nearest neighbor. And Voyager 1, the farthest human object ever launched, has spent 50 years crossing a distance so small relative to the interstellar gulf that it barely registers. It has covered less than 1,000th of the distance to the nearest star. At its current speed, it will take over 70,000 years to cover the rest. The interstellar void is not simply large. It is hostile to the idea of crossing. It resists travel not through active force, but through sheer, indifferent scale. There is no obstacle between here and Proxima Centauri, no barrier, no wall, just distance, and so much of it that our fastest machine, traveling continuously for 50 years, has covered a fraction so small it rounds to zero. And there is one more detail about our specific location that makes the emptiness feel almost personal. The region of interstellar space that Voyager 1 entered, the space immediately surrounding our solar system, is not typical. It is emptier than average. We live inside a void, within a void. Astronomers call it the local bubble. It is an irregularly shaped cavity in the interstellar medium, stretching roughly 300 to 600 light-years across, depending on direction, with narrow extensions reaching further through openings in the galactic plane. Inside this cavity, the density of interstellar gas drops to roughly 1/10 of the already sparse average for the galactic disk, where typical interstellar space contains about 1 atom per cubic centimeter. The interior of the local bubble contains roughly 1/10 of an atom per cubic centimeter. On average, only one particle drifts through every 10 cubic centimeters of this space. The space around us is not just interstellar vacuum, it is a pocket of deeper than usual interstellar vacuum, a region of exceptional emptiness even by the low standards of the galaxy's interior. The local bubble was not always here. It was carved out by violence. Over the last 10 to 20 million years, a series of roughly 15 to 20 supernova explosions in our stellar neighborhood detonated with enough energy to sweep the surrounding gas outward, compressing it into a dense shell at the bubble's edges and leaving the interior scoured clean. The result is a structure that we can map. X-ray observations and measurements of interstellar absorption toward nearby stars have allowed astronomers to trace the proximate boundaries of the local bubble in 3 dimensions. It is real, it is measurable, and we are inside it, sitting roughly in the interior. Not at the center, but not near the edge either. Embedded in a region of the galaxy where the emptiness that already defines interstellar space has been deepened by a recent history of stellar death. In 2022, a team led by astronomer Catherine Zucker at the Harvard-Smithsonian Center for Astrophysics published a study that revealed something remarkable about the bubble's edges. The expanding shell of compressed gas at the boundary of the local bubble is not merely a relic of past explosions, it is actively forming new stars. Zucker's team showed that essentially all of the major star-forming molecular clouds within roughly 500 light-years of the Sun, regions like the Taurus molecular cloud, the Ophiuchus cloud complex, and the Perseus molecular cloud, sit on the surface of the local bubble. They are not randomly distributed. They are arranged on the shell, in positions consistent with gas that was swept up and compressed by the expanding supernova-driven cavity. This means the emptiness around us created the nearest stellar nurseries. The supernovae that hollowed out the local bubble pushed gas outward until it piled up at the edges with enough density to collapse under its own gravity and begin forming new stars. The absence produced the conditions for new presence. The void made the cradles. It is a pattern that echoes, in miniature, a larger truth about how the universe organizes itself. Emptiness is not merely the space left behind when matter gathers elsewhere. It is an active participant in the process of cosmic organization. It shapes what forms at its boundaries. It determines where density can accumulate and where it cannot. Even here, in our own local neighborhood, the emptiness is not passive. It is formative. But the local bubble, for all its scientific interest, is a small thing by galactic standards. 1,000 light-years across in a galaxy 100,000 light-years wide. A pocket of relative emptiness in a disk that is itself almost entirely vacuum. It matters because it is ours. It is the specific emptiness we inhabit, the particular flavor of nothing that surrounds our particular star. And even this local nothing, this neighborhood-scale void, is emptier than any environment humans have ever created or experienced on Earth. When you sit in a quiet room at night and feel the silence, you are surrounded by 25 quintillion molecules per cubic centimeter pressing against your skin. When Voyager 1 drifts through the local bubble at 15 billion miles from home, it is surrounded by 1/10 of an atom per cubic centimeter. The difference between those two environments is so extreme that no metaphor can bridge it honestly. The quietest, stillest, most remote place on Earth, the bottom of the deepest ocean trench, the interior of the most isolated cave, is a raging storm of molecular activity compared to the tranquil, particle-starved emptiness of the local bubble. And this is still inside the galaxy. This is still the neighborhood. The emptiness between stars, which we have barely begun to describe, extends outward from here in every direction for light years upon light years, growing no denser, often growing thinner, stretching across the full disk of the Milky Way, with the uniformity of absence that makes the local bubble's particular emptiness feel almost indistinguishable from the general rule. Here is where the emptiness between stars becomes something more than a large number. It becomes a physical condition, a state of reality that defines what interstellar space actually is. Between our Sun and Proxima Centauri, there is almost nothing. Not figuratively, literally. The interstellar medium, the technical name for the material that exists between stars, has a density of roughly 1 atom per cubic centimeter. 1 atom. In a volume the size of a sugar cube. To understand how empty that is, compare it to the air you are breathing right now. At sea level on Earth, every cubic centimeter of atmosphere contains roughly 25 quintillion molecules. That is a 25 followed by 18 zeros. The interstellar medium is roughly 25 quintillion times less dense than the air in your lungs. To put that in perspective, a standard laboratory vacuum chamber, the kind used in semiconductor fabrication and many physics experiments, contains roughly 10,000 to 100,000 molecules per cubic centimeter. That is considered impressively empty by engineering standards. Interstellar space is tens of thousands of times emptier still. Only the most extreme vacuum systems ever built, such as the beam pipes inside gravitational wave detectors, approach the emptiness of the space between stars. And even those systems maintain that vacuum inside a sealed tube a few feet wide. The interstellar medium maintains it across trillions of miles in every direction, with nothing to contain it and nothing to disturb it. And that is the average density inside the galaxy, between stars that are relatively close together, in the spiral arms where matter is concentrated, in the neighborhoods where stars are born from collapsing clouds of gas, the emptiest regions between the arms, the long quiet stretches of galactic real estate where star formation has slowed or stopped, can be even more sparse. Densities of 1/10 of an atom per cubic centimeter are measured in those regions. You would need to search 10 sugar cubes worth of space to find a single atom. There is one exception to this rule of extreme sparseness, and the exception proves the point. Scattered unevenly through the galaxy are regions called molecular clouds, dense concentrations of gas and dust, where the interstellar medium has been compressed by gravity, shock waves from supernovae, or the spiral density waves that shape the galaxy's arms. These clouds are the birthplaces of stars. They are where gravity has pulled enough material together for nuclear fusion to ignite. Molecular clouds are, by interstellar standards, extraordinarily dense. A typical giant molecular cloud might contain a few hundred to a few thousand molecules per cubic centimeter. That sounds like a lot compared to the 1 atom per cubic centimeter of ordinary interstellar space. But consider what dense means here. A few thousand molecules per cubic centimeter is still roughly 10 quadrillion times less dense than Earth's atmosphere at sea level. The densest star-forming regions in the galaxy, the places where new suns are actively being born, are 10 trillion times emptier than the air in your lungs. And these dense regions are rare. Molecular clouds occupy roughly 2% of the Milky Way's total volume. 2%. 98% of the galaxy's volume is filled with the thinner, sparser interstellar medium that stretches between the clouds. Even inside a galaxy, even inside the structured, gravitationally organized disk of stars and gas that we call the Milky Way, matter is concentrated into a tiny fraction of the available space. The rest is near vacuum. The clouds themselves are temporary. They persist for roughly 10 to 30 million years before the stars they create either blow them apart with radiation and stellar winds or consume them through gravitational collapse. They are islands of relative density in an ocean of near nothing, and they dissolve on timescales that are short compared to the life of the galaxy. The Milky Way has been around for over 13 billion years. A molecular cloud lasts for a cosmic eye blink. The emptiness is permanent. The density is the interruption. So when you picture the galaxy in your mind, do not picture a solid disk of stars and glowing gas. Picture a vast, thin, mostly empty volume where 98% of the space contains roughly 1 atom per cubic centimeter or less, where the remaining 2% contains temporary clumps of gas that are themselves trillions of times emptier than the room you are sitting in, and where the stars born from those clumps are scattered so far apart that light takes years to travel between the nearest neighbors. That is the Milky Way. That is what a galaxy actually is. Not a dense river of light, but a nearly empty disk with luminous specks dotted through it at separations measured in trillions of miles. This is not a void in the way that word is normally used. A void implies the absence of something that should be there. Interstellar space is not missing anything. It is functioning exactly as it always has. The emptiness is not an error or a gap. It is the standard state of the galaxy's interior. Stars are the anomaly. Gas clouds are the anomaly. Planets, moons, asteroids, comets, every physical object you have ever heard of is the anomaly. The default condition between them is a vacuum so thorough that it outperforms every imitation humans have ever attempted. And scattered across that vacuum, at distances measured in trillions of miles, are the stars. Let us try to feel this in a different way. Forget the numbers for a moment. Imagine you are standing in the middle of a salt flat. An enormous white plain stretching to the horizon in every direction, perfectly flat, perfectly featureless. Now imagine someone places a single marble on that salt flat, 50 miles away from you. You cannot see it. You do not know it is there. Now imagine someone places another marble 70 miles away in a different direction, and another one 100 miles in a third direction. Each marble is a star. Each gap of 50, 70, 100 miles of empty salt flat is the interstellar medium. You are standing in the space between them. You could walk for days and find nothing. You could walk for weeks and encounter one marble if you were lucky. The flat is real. The marbles are real. But the flat is the overwhelming majority of what exists. And the marbles are so few and so scattered that the flat defines the landscape, not the marbles. Now scale that image up. The Milky Way contains somewhere between 200 billion and 400 billion stars. That sounds like a vast number. It is a vast number. But those stars are distributed across a disk roughly 100,000 light years in diameter and roughly 1,000 light years thick at the spiral arms. The volume of that disk is staggering, and when you divide the number of stars by the volume of space they occupy, the average distance between neighboring stars comes out to roughly 5 light years. 5 light years, roughly 29 trillion miles. Between every star and its nearest neighbor, on average, there is a gulf of almost 30 trillion miles of near-perfect vacuum. And 5 light years is the average. In the dense core of the galaxy, near the supermassive black hole called Sagittarius A star, stars are packed more tightly. The average separation in the galactic core drops to a fraction of a light year. But in the outer reaches of the spiral arms, in the quiet suburbs of the Milky Way where our sun happens to reside, the gaps are wider. Some stellar neighborhoods have separations of 8, 10, even 15 light years between nearest neighbors. Our own nearest neighbor, Proxima Centauri, happens to be closer than the average. We are, by galactic standards, living in a relatively populated area. And even here, the nearest star is 25 trillion miles away. To put the galaxy's emptiness into one stark image, If you removed every star from the Milky Way and replaced each one with a grain of table salt, and then you spread those grains across the volume of the galaxy at the correct relative distances, you would have a few 100 billion grains of salt scattered across a space tens of thousands of light years wide. You could search a volume the size of Earth's entire orbit around the Sun and find, on average, nothing. No grain, no salt, just space. The Milky Way is not a dense river of stars. It is a thin, scattered mist of pinpoints separated by abysses. When you see the Milky Way stretching across the sky on a dark night, you're looking along the plane of the disk, and the accumulated light of billions of distant stars merges into a continuous glow. But that glow is a trick of perspective. It is the same trick that makes a chain link fence look solid when you view it from a shallow angle. Head on, you can see through it easily. From the side, the overlapping links create the illusion of a solid barrier. The Milky Way's glow is the overlapping links. The space between them is almost everything. There is an experiment that illustrates this beautifully. In roughly 4.5 billion years, the Milky Way and the Andromeda Galaxy will collide. Andromeda is the nearest large galaxy to ours. It contains an estimated several 100 billion stars, roughly comparable to the Milky Way. It is approaching the Milky Way at roughly 250,000 miles per hour. The two galaxies will merge over the course of several billion years, their stars and gas clouds mixing together into a single larger galaxy, sometimes called Milkomeda. When that collision happens, despite the fact that hundreds of billions of stars from each galaxy will pass through the other, the probability of any two stars directly hitting each other is essentially zero. Not low, not unlikely. So close to zero that astronomers do not seriously plan for it. The stars will slide past each other like raindrops falling through a forest canopy. Each raindrop is real. Each branch is real. But there's so much space between the branches, and each raindrop is so small relative to the gaps, that almost nothing makes contact. Two entire galaxies, each containing hundreds of billions of stars, will pass through each other and barely notice. That is how empty a galaxy is on the inside. That is how much space exists between the points of light that make it look, from a distance, like a solid wheel of fire. Now consider what it means that this internal emptiness is the crowded version. Galaxies are where matter has concentrated. They are the dense regions, the places where gravity pulled gas together, ignited nuclear fusion, and built the structures we call stars, planets, and solar systems. Relative to the space between galaxies, the interior of a galaxy is a thriving, bustling, matter-rich environment. The space between galaxies is worse, far worse, and it is worth understanding just how much worse, because the transition from interstellar to intergalactic emptiness is not a gentle slope. It's a cliff. Inside the Milky Way, the interstellar medium has a density of roughly 1 atom per cubic centimeter. Between galaxies, in the intergalactic medium, the density drops to roughly 1 atom per cubic meter. That is a factor of 1 million. Intergalactic space is approximately 1 million times emptier than the space between stars, and the space between stars is already 25 quintillion times emptier than the air you breathe. Stack those numbers. The air in your lungs is dense. The space between stars is 10 quintillion times less dense. And the space between galaxies is another million times less dense than that. The intergalactic medium is so rarefied that it barely qualifies as existing. Fewer than 1 atom per cubic meter means that if you held out a box the size of a refrigerator in intergalactic space, it would contain On average, nothing. You would need to check several refrigerator-sized volumes before you found a single hydrogen atom drifting alone in the dark. This is the reality between every galaxy and its neighbors. Between the Milky Way and Andromeda, there are 2.5 million light years of this. 2.5 million light years where every cubic meter contains roughly one atom. Where the temperature of the gas, if you can call it gas, reaches millions of degrees, not because anything is burning, but because the particles are so sparse that the few that exist carry enormous individual energy. You would not feel the heat. There are not enough particles to transfer warmth to your skin. You would freeze to death in intergalactic space while surrounded by gas that is technically hotter than the surface of most stars. The emptiness is so extreme that the normal rules of thermal experience break down entirely. And Andromeda is close. It is our nearest large galactic neighbor. Other galaxies are tens of millions of light years away. Hundreds of millions. Billions. The most distant galaxies observed by the James Webb Space Telescope are over 13 billion light years from Earth. The light we see from them left when the universe was less than 400 million years old. It has been traveling across intergalactic vacuum for over 13 billion years, crossing space where there is effectively nothing to interact with, nothing to absorb it, nothing to scatter it, just vacuum, for 13 billion years. This is the medium through which all of our observations of the distant universe travel. Every photon from every galaxy arrives after crossing an abyss of nearly perfect emptiness that dwarfs the distances inside any single galaxy by factors of thousands or millions. The intergalactic medium is not a gap between objects. It is the dominant volume of the universe. If you picked a random point in the observable cosmos, the overwhelming probability is that you would land in intergalactic space, not inside a galaxy, not near a star, not on a planet, in the void between structures, surrounded by less than one atom per cubic meter, in a darkness so complete that the nearest source of visible light might be millions of light years in any direction. That is what most of the universe actually looks like. Not the photographs, not the telescope images, not the artist's impressions of colourful nebulae and spiral galaxies. Those images represent the vanishingly small fraction of reality where something is happening. The rest, the overwhelming majority, looks like nothing, is nothing. By every measurable standard, is as close to absolute emptiness as the laws of physics allow. And yet there is a structure to this emptiness. That is perhaps the most unsettling part. The galaxies are not scattered randomly. They are arranged. They follow a pattern, a vast three-dimensional web of filaments and walls and clusters, connected by threads of matter and separated by enormous, underdense regions, where even the thin scattering of galaxies thins further into almost total absence. The emptiness is not uniform. It has shape, it has architecture, it is organized. And the organized emptiness is far larger than the organized matter. This is where the picture changes character. Up to this point, we have been talking about the gaps between things, the space between planets, the vacuum between stars, the abyss between galaxies, each one larger and emptier than the last. But at the next scale, the emptiness stops being the space between objects and starts being the space itself. It becomes the defining structural feature of the cosmos. It becomes the thing that the universe is mostly made of. That transition is what separates a story about large distances from a story about the fundamental nature of reality. And that transition begins with a map. The largest, most detailed three-dimensional map of the universe ever constructed. A map that does not show you where things are. It shows you where things are not. And what it reveals is that emptiness is not the background. It is the architecture. In 1989, astronomers at the Harvard-Smithsonian Center for Astrophysics published a map that changed how scientists understood the universe. It was called the CFA Redshift Survey, and it was one of the first attempts to chart the three-dimensional positions of galaxies across a large region of the cosmos. Previous maps of the sky had been flat, two-dimensional projections. This one used the redshift of each galaxy's light, the stretching of its wavelengths caused by the expansion of the universe, to estimate how far away each galaxy actually was. For the first time, astronomers could see depth. What the map revealed was not a uniform scattering of galaxies. It was not random. It was not a smooth, even distribution of matter gradually thinning in every direction. It was a pattern. Galaxies were arranged along thin sheets and long filaments, concentrated in clusters at the intersections, and separated by vast regions where almost nothing existed. The structure looked like the surface of soap bubbles pressed together, where galaxies cling to the bubble walls, and the interiors are hollow. The hollow regions had a name. They were called cosmic voids, and they were enormous. The CFA survey was limited. It covered only a thin slice of the sky. But even in that slice, the voids were obvious. They stretched across tens of millions of light years, regions of space where the density of galaxies dropped to a fraction of the cosmic average. Where a typical volume of the universe might contain hundreds or thousands of galaxies, these regions contained almost none. They were not small gaps between clusters. They were continent-sized absences in a universe that, at smaller scales, had seemed relatively structured. In the decades that followed, larger and more detailed surveys confirmed and expanded the picture. The 2-degree field galaxy redshift survey in the early 2000s mapped over 200,000 galaxies. The Sloan Digital Sky Survey, running from 2000 through the 2010s, mapped over 1 million. And in 2026, the Dark Energy Spectroscopic Instrument completed its 5-year primary survey after mapping more than 47 million galaxies and quasars, producing the largest three-dimensional map of the universe ever constructed. Every one of these surveys told the same story. The universe has a structure. That structure is called the cosmic web. And the defining feature of the cosmic web is not the matter that forms it. It is the emptiness that surrounds it. The cosmic web is built from 4 types of structure. The densest are galaxy clusters, massive gravitationally bound collections of hundreds or thousands of galaxies sitting at the nodes where multiple filaments converge. Connected to those clusters are the filaments themselves, long threads of galaxies and gas stretching across tens or hundreds of millions of light years, forming the skeleton of the web. Between the filaments are walls, thinner sheets of galaxies that create 2-dimensional surfaces enclosing large volumes, and inside those enclosed volumes, surrounded by walls and filaments and clusters, are the voids. The voids are the largest structures in the observable universe, not the clusters, not the filaments, the voids. They range from roughly 30 million to more than 300 million light years across. Some are spherical, some are elongated. Some connect to neighboring voids through narrow tunnels where the walls between them have thinned to almost nothing. Together, they fill the majority of the universe's volume, Estimates vary depending on how void boundaries are defined, but the consensus among cosmologists is that cosmic voids account for somewhere between 60 and 80% of the total volume of the observable universe. That number deserves to be repeated. Between 60 and 80% of the volume of the observable universe is void. Not filled with thin gas, not lightly populated with scattered galaxies. Void. Regions where the density of matter drops to less than 20% of the cosmic average. Regions where a volume that should contain thousands of galaxies contains a handful or fewer. The galaxies, the filaments, the clusters, all the structure that surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument have mapped so carefully, all of that lives in the remaining 20 to 40% of the volume. The matter that makes up every star, every planet, every living thing, every atom you have ever encountered, exists within a thin lattice occupying the minority fraction of reality. The majority is void. The most famous void in astronomy was discovered in 1981 by astronomer Robert Kirshner and his colleagues during one of the earliest redshift surveys. They were mapping galaxies in 3 fields of view near the constellation Boötes when they noticed something strange. In all 3 fields, there was an identical gap in the distribution of galaxies at the same distance. A hole, not a small hole, an enormous one. It became known as the Boötes void, and for decades it was considered the largest known void in the observable universe. It spans roughly 330 million light-years across. Inside that volume, astronomers would normally expect to find approximately 2,000 galaxies. They found roughly 60. 60 galaxies scattered through a sphere of space 330 million light-years wide. Most of those 60 are arranged in a loose tube-shaped strand running through the center of the void, as if even the few galaxies that exist there are clinging to the last remnant of a filament that otherwise dissolved into nothing. To appreciate the scale of the Boötes void, consider that the Milky Way is roughly 100,000 light-years across. The Boötes void is more than 3,000 times wider than our entire galaxy. You could line up over 3,000 Milky Ways end to end, and they would barely span the diameter. And inside that enormous volume, there are fewer galaxies than there are people in a small office building. If you were on a planet inside the Boötes void, far from the thin central strand of galaxies, and you looked up at your night sky, you might see almost nothing. No Milky Way stretching overhead, no bright galaxies nearby. Perhaps a few faint smears of distant light in a handful of directions, and in every other direction, unbroken blackness stretching to the edge of visibility. The sky would look essentially empty. You could be forgiven for concluding that the universe contained almost nothing at all. The Boötes void is not unique. It is simply one of the largest and best studied examples. The universe is filled with voids. Some are smaller, spanning 30 or 40 million light-years. Some are comparable in size. A few may be even larger. The Eridanus supervoid, linked to the cold spot in the cosmic microwave background, may span over 500 million light-years, though its precise boundaries and depth are still debated. The Eridanus supervoid deserves more than a passing mention because it illustrates something crucial about cosmic emptiness. It is not just empty, it leaves marks. The Eridanus supervoid is a vast underdense region, roughly centered on the constellation Eridanus. Estimates of its size vary, but it may span 500 million to over a billion light years across. It was identified in part because of an anomaly in the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky at microwave wavelengths. The cosmic microwave background is remarkably uniform. It is the same temperature in every direction to within roughly 1 part in 100,000. Those tiny temperature variations, mapped in exquisite detail by the Planck satellite and earlier missions, are the fossilized fingerprints of density fluctuations in the early universe, the seeds that eventually grew into the cosmic web. They are extraordinarily small, on the order of millionths of a degree. But in one region of the sky, in the direction of Eridanus, there is a cold spot, an area where the cosmic microwave background temperature is measurably lower than the surrounding sky, by a larger amount than the standard fluctuations can comfortably explain. The spot is not enormous on the sky. It spans roughly 5 degrees, roughly 10 times the apparent diameter of the full moon. But it corresponds to a region of space that is physically vast, and its temperature deficit has puzzled cosmologists since it was first identified by the Wilkinson Microwave Anisotropy Probe in 2004. One leading explanation is that the cold spot is the imprint of the Eridanus supervoid on the cosmic microwave background. The mechanism is called the integrated Sachs-Wolf effect. When photons from the cosmic microwave background travel through a region of space that is underdense, they lose a tiny amount of energy. In a universe without dark energy, they would regain that energy as they climbed out of the void on the other side. But in a universe where dark energy is causing the void to expand while the photons are crossing it, the void is slightly larger when the photons exit than when they entered. The photons lose a fraction of their energy permanently. The result is a subtle cooling of the microwave background in the direction of the void. This effect is small. It accounts for only a fraction of the observed cold spot anomaly, and some researchers argue that the Eridanus supervoid alone cannot fully explain the temperature deficit. Other factors may contribute, including statistical flukes in the random distribution of primordial fluctuations. The debate is ongoing, but the principle itself is confirmed. Cosmic voids are not invisible to the oldest light in the universe. They leave imprints. The emptiness is not just structurally dominant, it physically alters the radiation that passes through it, stamping its signature onto the cosmic microwave background in a way that could be measured from Earth 13.8 billion years later. The voids are not passive absences. They are active regions of space-time that interact with everything that crosses them, including the light from the dawn of the universe itself. And then there is the structure that makes all of these look modest. The KBC void, named after astronomers Keenan, Barger, and Cowie, who characterized it in a 2013 study, is a region of underdensity roughly 2 billion light-years in diameter. It is not as deeply empty as the Bootes void. Its density is estimated at roughly 15 to 20% below the cosmic average, meaning it contains fewer galaxies per unit volume than a typical region of the universe, but not dramatically fewer. What makes the KBC void significant is not its depth, it is its location. We are inside it. The Milky Way, our Sun, Earth, everything within our local group of galaxies sits within the KBC void. We are not at the edge, we are not near the boundary. We are embedded within a vast underdense region that stretches roughly 1 billion light years in every direction. The universe around us, the local universe that we have studied most carefully and for the longest time, is emptier than average. The cosmic neighborhood we call home is a void. This discovery has implications that extend beyond simple geography. Some researchers have proposed that the KBC void may contribute to one of the most stubborn problems in modern cosmology: the Hubble tension, the persistent disagreement between different methods of measuring how fast the universe is expanding. If we are living inside a void, the local expansion rate we measure might be slightly higher than the true cosmic average, because matter inside voids moves outward faster than matter in denser regions. Our measurements of cosmic expansion may be subtly distorted by the emptiness we happen to inhabit. Whether this explanation fully resolves the Hubble tension remains an open question, but the possibility itself is remarkable. The emptiness surrounding us might not just be a backdrop. It might be actively shaping the data we use to understand the cosmos. The void is not passive. It is a participant. Before we go further outward, it is worth understanding the structure that lies between our local group of galaxies and the vast cosmic voids. Because there's a scale of organization between individual galaxies and the full cosmic web that makes the architecture of emptiness even more vivid. In 2014, a team led by astronomer Brent Tully published a landmark study defining the boundaries of our home supercluster. They called it Laniakea, a Hawaiian word meaning immense heaven. Using data on the velocities of galaxies in our region of the universe, they mapped the gravitational basin of attraction, the region of space within which galaxies are flowing toward a common center, rather than being carried apart by cosmic expansion. Laniakea is enormous. It spans roughly 500 million light-years across and contains approximately 100,000 galaxies. The Milky Way sits near its outer edge, far from the gravitational center, which lies in the direction of a region astronomers have long called the Great Attractor. The Great Attractor is not a single object. It is the concentration of mass, a knot in the cosmic web where multiple filaments converge, pulling galaxies toward it from hundreds of millions of light years in every direction. The discovery of a Laniakea was celebrated as a breakthrough in understanding our cosmic address. For the first time, astronomers could say not just which galaxy we live in, but which supercluster, which flow pattern, which gravitational neighborhood. It gave us a sense of place on a scale that had previously been too large to map coherently. But here is what the celebration often overlooked. Laniakea is mostly empty. 100,000 galaxies sounds like a large number. Spread across a volume 500 million light-years wide, it is a whisper. The galaxies within Laniakea are arranged along filaments and walls that occupy a small fraction of the total volume. The rest is void. Smaller voids, local underdensities, pockets of space tens of millions of light-years across where the galaxy count drops to nearly zero. It is a label applied to a region of the cosmic web, and the cosmic web, even in a region that contains 100,000 galaxies, is still overwhelmingly composed of nothing. Our cosmic address does not place us inside a crowded structure. It places us inside a labeled region of the web, where the filaments are close enough to share a gravitational flow. The spaces between those filaments are as empty as the spaces between filaments anywhere else in the universe. We belong to Laniakea in the same way a single spider belongs to the web it sits on. The web is real. The connections are real. But the web is mostly air. And the most recent science suggests that participation runs deeper than anyone expected. In March of 2026, researchers published findings showing that cosmic voids are not simply empty regions left behind as matter gathered into filaments and clusters. They are active. Within them, a force called dark energy, the mysterious component that makes up roughly 68% of the total mass energy content of the universe, becomes the dominant influence. In the dense regions of the cosmic web, gravity from matter overwhelms dark energy's effect. But inside voids, where matter is scarce and gravity is weak, dark energy has free reign. The result is that voids expand. They push outward, stretching the space inside them, thinning whatever faint traces of matter remain, and pressing against the walls and filaments at their borders. Over immense spans of time, this process slowly tears the cosmic web apart. The intricate lattice of filaments and clusters that gives the universe its structure is being pulled apart from the inside by the expanding voids. The universe is not simply empty, its emptiness is growing. The voids are getting larger. The filaments are getting thinner. The walls are weakening. The clusters, held together by their own gravity, will persist for a long time. But the connections between them, the delicate threads of the cosmic web that link one structure to the next, are under constant outward pressure from the expanding nothing between them. This is a structural truth that goes far beyond space is big. The universe is not a stable container with objects scattered inside it. It is a dynamic system where the emptiness itself is an active force, and that force is winning. Over billions of years, the cosmic web will dissolve. The filaments will thin beyond detection. The walls will evaporate. The voids will merge into a single expanding emptiness, interrupted only by isolated clusters, each one a gravitational island drifting further from every other island, as the space between them stretches without limit. That is the long-term future of cosmic structure. Not collapse, not concentration, dissolution, separation, the slow victory of nothing over something. And this future is not speculative. It is the direct consequence of observations confirmed by multiple independent surveys. The Dark Energy Spectroscopic Instrument's 3-year analysis, published in 2025, strengthened evidence that dark energy may not even be constant. It may be evolving, weakening over cosmic time, which introduces new uncertainty into predictions about the universe's ultimate fate, but does not change the fundamental trajectory. Whether dark energy remains constant or diminishes, the voids will continue to expand. The separations will continue to grow. The architecture of the universe will continue to be defined primarily by the empty spaces rather than the matter within them. There is one more detail about cosmic voids that rarely appears in popular science discussions, but that reinforces the thesis in a way nothing else can. The galaxies that do exist inside voids are different from the galaxies that exist in denser regions. They are changed by the emptiness around them. Void galaxies tend to be smaller than galaxies in clusters or along filaments. They tend to be bluer, meaning they are forming stars at a relatively higher rate compared to their mass. They tend to be richer in gas and poorer in the older stellar populations that dominate galaxies in crowded environments. And they tend to be more isolated, obviously, but also more undisturbed. Galaxies in dense regions are constantly interacting with neighbors. They collide, merge, strip gas from each other, and trigger bursts of star formation through tidal forces. Galaxies and voids experience almost none of this. They evolve in isolation, shaped only by their own internal processes and the slow, quiet influence of the near-empty space surrounding them. In a sense, Void galaxies are what galaxies look like when the universe leaves them alone. They are the control group in a cosmic experiment about the effects of environment on galactic evolution. And what the control group shows is that galaxies in isolation are simpler, quieter, and less massive than their counterparts in the cosmic web's dense intersections. The environment of emptiness produces a different kind of galaxy. The void does not merely surround its contents, it shapes them. It determines what they become. This is a subtle but important point. Emptiness is not just the absence of influence, it's itself an influence. A galaxy born in a void will evolve differently, look differently, and age differently than a galaxy born in a cluster. Not because something acted on it, but because nothing did. The lack of interaction, the lack of neighbors, the lack of gravitational disturbance. These absences are themselves formative forces. The emptiness is not neutral. It produces outcomes. It molds the objects it contains through the simple mechanism of withholding everything that denser environments provide. When you consider that voids fill the majority of the universe's volume, this means that most of the environments in the observable cosmos are environments of absence. The default galactic experience, if you could somehow average across all the galaxies in the universe, weighted by the volume of space they inhabit, is isolation. Cluster galaxies, the ones we study most often because they are brightest and easiest to find, are the outliers. They are the ones living in the unusual conditions. The void galaxies, small and quiet and alone, are closer to the cosmic norm. Even the galaxies that exist inside the emptiness are shaped by it. Even matter, where it manages to persist inside a void, carries the signature of the nothing that surrounds it. The architecture of absence does not just define the spaces between things, it defines the things themselves. Now, step back and consider what all of this means in aggregate. We began at the scale of the solar system, where the distances between planets revealed a system that is almost entirely vacuum. We moved to the interstellar scale, where the gaps between stars turned out to be trillions of miles of near-perfect emptiness, far more rarefied than any laboratory vacuum. We crossed into intergalactic space, where the density dropped another factor of 1,000,000 to less than 1 atom per cubic meter. And now we have arrived at the scale of the cosmic web itself, where the majority of the universe's volume is void, where the structures that contain all the matter we have ever observed occupy the minority fraction, where the emptiness is not a background condition but a structural force that is actively reshaping the cosmos. At every scale, the same pattern repeats. The objects are small, the distances are large, the emptiness is dominant, and the further out you go, the more dominant it becomes. The solar system is mostly empty. The galaxy is more empty than the solar system. Intergalactic space is more empty than the galaxy. And the cosmic voids that define the large-scale structure are the emptiest environments that exist in the observable universe, filling the majority of its volume with a near absence of matter that makes even intergalactic space look crowded by comparison. And then there is the composition problem. Everything we have discussed so far, every star, every planet, every atom of gas drifting through interstellar or intergalactic space, all of it belongs to a category called baryonic matter, ordinary matter, the kind made of protons, neutrons, and electrons, the kind that makes up your body, the air you breathe, the ground you stand on, and the stars you see in the sky. Baryonic matter constitutes roughly 5% of the total mass energy content of the universe. 5%. Everything that has ever been photographed, studied, touched, measured, or observed by any telescope at any wavelength across the entire history of astronomy, all of it belongs to a category that accounts for 1/20th of what the universe contains. The other 95% is composed of dark matter, roughly 27%, and dark energy, roughly 68%. Dark matter does not emit, absorb, or reflect light. It interacts with ordinary matter only through gravity. We know it exists because galaxies rotate faster than they should based on their visible mass, and because the cosmic web structure requires more gravitational scaffolding than baryonic matter alone can provide. But we cannot see it. We cannot touch it. We do not know what it is made of. Dark energy is even more mysterious. It is the force driving the accelerating expansion of the universe, the force that dominates inside cosmic voids and slowly tears the web apart. We do not know its nature. We do not know why it has the value it has. We do not know whether it is truly constant or evolving. The dark energy spectroscopic instrument's recent results suggest it may be changing over time, but the evidence is not yet conclusive. Together, dark matter and dark energy constitute 95% of the universe's content, and we cannot see either one. We cannot detect them directly. We infer their existence from their effects on the 5% we can observe. This means that the visible universe, the universe of light and matter and structure, is not just sparse. It is a thin residue, a trace element. The overwhelming majority of reality is composed of substances we cannot see and do not understand, filling a volume that is itself overwhelmingly empty of even those invisible substances. The cosmic web, the grandest structure we have ever mapped, is built from the 5%. The voids that surround it are dominated by the 68%, and the 27% provides invisible scaffolding that we can only detect through its gravitational shadow. The universe is not full of things. It is full of emptiness and mystery, with a thin, fragile, luminous skin of matter stretched across it like a film of oil on the surface of an ocean. The oil catches the light. The oil is what we photograph and study and marvel at. But the ocean underneath is almost everything, and it is made of substances we cannot name. This is the architecture of reality at the largest scale we can observe. A web of matter so thin that it occupies the minority of the volume, voids so vast that they fill the majority, a composition so dominated by invisible components that the visible universe is a rounding error in the total accounting, and an expansion so relentless that the already vast separations between structures are growing year by year at an accelerating rate. The universe was not built as a crowded room. It was built as a framework of thread-like structures, stretched across an emptiness so vast that the threads themselves are barely there. The objects we see, the galaxies and stars and planets, are not the universe. They are decorations on the scaffolding, and the scaffolding is surrounded on every side by nothing. That is not a poetic metaphor. It is a physical description of the observable cosmos, confirmed by every major survey of large-scale structure conducted in the last 4 decades. The emptiness is not the background to the story. It is the story. It is the dominant condition at every scale, growing more dominant as the scale increases, and it is getting worse, and that changes what it means to exist here. Not in a vague emotional sense, in a structural, physical, measurable sense. Because once you understand that the universe is organized primarily around absence, the question shifts. It is no longer about what is out there. It is about what it means that almost nothing is. There's a photograph taken by the Cassini spacecraft in 2013 that does something no other image in the history of science has ever done quite as well. Cassini was orbiting Saturn, nearly 900 million miles from Earth, when mission controllers instructed it to turn its cameras back toward the inner solar system. The resulting image shows Saturn's rings in the foreground, backlit by the distant sun, glowing like a crescent of pale gold. And there, beneath the rings, almost lost in the glare, is a tiny point of light, smaller than a pixel, barely distinguishable from the background noise of the detector. That point is Earth. Everything you have ever known, every person who has ever lived, every war, every symphony, every birth and death and revolution and discovery, every ocean, every mountain, every city and forest and desert, all of it reduced to a fraction of a single dot in a photograph taken from the orbit of the sixth planet. Carl Sagan described a similar image, the pale blue dot photograph taken by Voyager 1 in 1990, as a reminder of how small and fragile our world is. But the Cassini image adds something that the Voyager photograph could not: context. In the Cassini image, you can see the rings of Saturn stretching across the frame. You can see the blackness of space surrounding everything. You can see the scale. And what the scale tells you is not just that Earth is small, it is that Earth is alone. Between that dot of light and the camera that photographed it, there is almost 900 million miles of nothing. No waypoint, no landmark, no rest stop, nothing to break the emptiness, just vacuum, stretching in every direction, separating everything from everything else. That is the solar system, the smallest scale of emptiness we have discussed. And we already know it gets worse from there. But what remains is not about adding more zeros to the distance. It is not about finding a bigger void or a longer gap or more extreme measurement of how little matter exists per cubic meter. The numbers have been laid out, the scales have been walked, the architecture has been described. What remains is the question that the architecture raises. A question that is not scientific in the traditional sense, but that emerges directly from the science, unavoidably and without comfort. What does it mean to exist in a universe where the dominant condition is separation? Every human culture that has ever looked at the sky constructed stories about connection. The stars were gods watching over us. The constellations were maps, guides, companions in the dark. The Milky Way was a river, a road, a bridge between worlds. The sky was full, and its fullness meant something. It meant we were seen. It meant we were part of a larger whole. It meant the universe was, in some fundamental way, a place where things belong together. The science we have covered tonight dismantles that story at every level. At the planetary scale, the objects in our solar system are separated by tens of millions to billions of miles of vacuum. At the stellar scale, the nearest star is 25 trillion miles away across a void more empty than any vacuum humans have ever produced. At the galactic scale, the stars within our own Milky Way are scattered so thinly that two entire galaxies can pass through each other without a single collision. At the intergalactic scale, the space between galaxies is 1,000,000 times emptier than the space between stars. And at the cosmic scale, the voids that fill the majority of the observable universe make intergalactic space look dense. At no point in this progression does the emptiness diminish. At no point does the universe become fuller. The pattern is monotonic and relentless. Each increase in scale reveals more emptiness, not less. The further out you look, the more the universe resembles what it mostly is: a vast, structured nothingness with matter clinging to its edges in quantities so small they barely register against the total volume. This is not a flaw in the universe. That is the part that takes the longest to absorb. The emptiness is not a problem to be solved. It is not a gap waiting to be filled. It is not a failure of some process that should have produced more matter or distributed it more evenly. The emptiness is the outcome of the same physical laws that produce stars and galaxies and planets and life. Gravity pulled matter together into dense structures. The spaces between those structures emptied. The expansion of the universe stretched those spaces further. Dark energy accelerated the stretching, and the result, after 13.8 billion years of cosmic evolution, is a universe where the overwhelming majority of the volume contains almost nothing, and the tiny fraction that contains something is organized into thin threads and fragile clusters separated by abysses that are growing wider every second. The laws of physics didn't build a full universe. They built a sparse one. The sparseness is not incidental. It is structural. It is the direct, predictable, mathematically inevitable consequence of how gravity, expansion, and dark energy interact across cosmic time. A universe that began with a nearly uniform distribution of matter and energy 13.8 billion years ago was always going to evolve into a web of filaments surrounded by voids. The emptiness was written into the initial conditions. It was there from the beginning, encoded in the density fluctuations of the early cosmos, waiting to emerge as the universe expanded and cooled, and matter began to fall inward toward the slight overdensities that would become clusters and galaxies. We are not living in a universe that happens to be empty. We are living in a universe that was always going to become empty. The emptiness is not an accident, it is the architecture. And that architecture has consequences for how we think about our place within it. Humans are social creatures. We evolved in groups. Our brains are wired for connection, for proximity, for the expectation that reaching out will result in contact. When we imagine the universe, we instinctively project that expectation onto the cosmos. We imagine that civilizations might communicate across the stars. We imagine that someday we might travel to other worlds and find neighbors. We imagine that the universe, like our evolutionary environment, is a place where connection is possible if you are willing to make the effort. The structural reality of the cosmos does not support that expectation. The nearest star is 4.25 light years away. A radio signal sent today would arrive there in 4.25 years. A reply would take another 4.25 years. An entire conversation consisting of one question and one answer would take 8.5 years. A conversation with even the most modest back and forth would span decades. And that is the nearest star. Most stars in the galaxy are hundreds or thousands of light years away. A signal sent to the center of the Milky Way would take 27,000 years to arrive. A signal sent to Andromeda would take 2.5 million years. These are not engineering problems waiting for better technology. They are structural features of the universe. The speed of light is not a limitation imposed by our current level of development. It is a fundamental property of space-time. Nothing that carries information can exceed it. No signal, no spacecraft, no communication of any kind can travel faster than roughly 186,000 miles per second. And at that speed, the distances between objects in the universe impose delays so long that the concept of conversation, of connection, of real-time interaction between distant points becomes physically meaningless at any scale beyond our immediate cosmic neighborhood. If intelligent life exists elsewhere in the Milky Way, and statistically it seems reasonable that it might, the distances separating us from any such civilization are almost certainly measured in hundreds or thousands of light years. Even at the speed of light, contact would require centuries or millennia in each direction. The civilizations involved would rise and fall between messages. Languages would change. Cultures would evolve beyond recognition. The sender and the receiver would be, in every meaningful sense, strangers to each other by the time a reply arrived. And that is within a single galaxy. Between galaxies, the situation is not just difficult, it is hopeless. The expansion of the universe means that distant galaxies are receding from us faster than light. Not because they are moving through space faster than light, but because the space between us is stretching. Galaxies beyond a certain distance, called the cosmic event horizon, are already unreachable. No signal sent from Earth today, no matter how powerful, will ever reach them. They are causally disconnected, existing in a region of the universe that is, for all practical and physical purposes, in a separate reality from ours. We can see their light because that light was emitted long ago when they were closer. But we can never touch them, visit them, or communicate with them. They are gone. And the number of galaxies beyond our cosmic event horizon is growing. As the expansion accelerates, more galaxies cross the threshold every moment. The observable universe is shrinking in terms of what we can ever hope to interact with, even as it continues to grow in terms of what we can still see. The light is arriving. The galaxies it came from are already out of reach. This is the loneliest implication of cosmic emptiness. It is not that the universe is empty right now. It is that the universe is becoming more empty, more disconnected, more structurally isolated with every passing moment. The voids are expanding. The filaments are thinning. The galaxies at the edges of our observable universe are sliding past the horizon into permanent inaccessibility. The architecture of separation is not static. It is dynamic. It is accelerating. The universe is pulling itself apart, and the process has been underway for billions of years and will continue for billions more. In the deep future, trillions of years from now, the expansion will have carried every galaxy beyond the observable horizon of every other galaxy. An astronomer living in the Milky Way at that time, if such a being could exist, would look out at the sky and see nothing. No Andromeda, no Virgo cluster, no cosmic web. The sky would be black and empty in every direction, and there would be no evidence that anything else had ever existed. The universe would appear to contain a single galaxy, alone in an infinite void, with no way to determine that it had ever been otherwise. And even that galaxy will not last. Stars are not permanent. They burn fuel. They exhaust it. They die. The most massive stars, the blue giants that blaze with 100,000 times the luminosity of our sun, burn through their hydrogen in a few million years and explode or collapse. Sun-like stars last roughly 10 billion years. Our own sun is approximately halfway through its main sequence lifetime. In roughly 5 billion years, it will swell into a red giant, engulf the inner planets, and eventually shed its outer layers to leave behind a white dwarf. A dense remnant the size of Earth that will slowly cool over trillions of years toward absolute darkness. The longest-lived stars are the red dwarfs. Small, dim, and miserly with their fuel, they can burn steadily for trillions of years, far longer than the current age of the universe. A red dwarf born today will still be shining when the cosmos is 100 times older than it is now. But even red dwarfs are not eternal. They too will eventually exhaust their hydrogen. The fusion will stop, the light will go out, and no new stars will replace them. Star formation requires gas. The raw material, the molecular hydrogen that collapses under gravity to ignite nuclear fusion, is a finite resource within any galaxy. The Milky Way is currently converting roughly 1 to 2 solar masses of gas into stars each year. That rate is already declining from what it was billions of years ago. The peak of cosmic star formation occurred roughly 10 billion years in the past. The universe is already past its most productive era. The lights are not turning on as fast as they used to. They have been dimming, in aggregate, for the majority of cosmic history. In roughly 100 trillion years, give or take, the last red dwarfs will exhaust their fuel. The last stellar furnaces in the galaxy will cool and fade. No new stars will form because there will be no gas left to form them. The Milky Way, or whatever merged remnant it has become by then, will go dark. Not dim, dark. A galaxy of stellar corpses, white dwarfs fading toward black, neutron stars spinning down to silence, and black holes sitting in the emptiness, feeding on nothing because there is nothing left to consume. This era, which physicists call the degenerate era, will last far longer than the current age of the universe. The white dwarfs will take trillions upon trillions of years to cool completely. The black holes will persist even longer, slowly evaporating through a process called Hawking radiation, losing mass one particle at a time over timescales so vast that the numbers lose all human meaning. A stellar mass black hole would take roughly 10 to the 67th power years to evaporate. A supermassive black hole like Sagittarius A star would take roughly 10 to the 87th power years. The most massive black holes in the universe, those containing tens of billions of solar masses, would take roughly 10 to the 100th power years. These numbers are not billions or trillions. They are numbers so large that writing them out in full would fill pages with zeros. And after even the black holes are gone, what remains is a universe of sparse, cooling particles drifting through an emptiness that has expanded beyond all recognition. Photons stretch to wavelengths longer than the observable universe. Electrons and positrons so far apart that they will never interact with another particle again. A cosmos where the concept of structure has ceased to apply, where there are no objects, no boundaries, no regions of higher or lower density, just an even, featureless, near-absolute emptiness extending in every direction without limit and without change. This is not a dramatic ending. It is not a bang or a crunch or a sudden catastrophe. It is a slow fade, a dimming so gradual that if consciousness could somehow persist through it, the loss would be imperceptible from one eon to the next. Each era quieter than the last. Each epoch emptier than the one before. The universe does not end with violence. It ends with distance. The same distance that already defines reality at every scale we have examined, carried forward to its logical, thermodynamic, inevitable conclusion. The emptiness that we have traced from the solar system to the interstellar medium, to the intergalactic void, to the cosmic web, is not a static condition. It is a trajectory. The universe was less empty in the past. It is more empty now. It will be more empty still in the future. And in the far unimaginable future, it will be empty in a way that makes the current cosmic voids look crowded. The direction has never changed. The arrow points one way, toward separation, toward silence, toward a cosmos where the last traces of structure dissolve into a uniformity of nothing that will persist, as far as physics can project, forever. That is the full arc of cosmic emptiness, not a snapshot, a story. A story that began with slight density variations in the infant universe, passed through an era of structure and light and complexity that we happen to inhabit, and ends in a darkness so total and so permanent that the current age of stars will be remembered, if memory is even a coherent concept, as a brief, bright anomaly in an eternity of void. That future astronomer would not be wrong about what they observe. They would simply be living in a universe where the evidence of connection has been erased by expansion. The other galaxies would still exist. They would still contain stars and planets and perhaps civilizations of their own. But the distance between them would be so vast and growing so quickly that no information could ever cross it. Each galaxy would be an island universe in the most literal and permanent sense. Isolated not by technology or will, but by the geometry of space-time itself. That scenario is trillions of years away. It is not our immediate concern, but it is the logical endpoint of the process that is already underway. The same force that is expanding the voids today, the same dark energy that dominates the emptiest regions of the cosmos and slowly tears the cosmic web apart, that force does not stop. It does not reverse. It continues, and its consequence is increasing isolation on every scale. This is the deep terror of cosmic emptiness. It is not a fear of the dark. It is not a fear of what might be lurking in the void. It is the recognition that the void is not a threat. It is the structure. It is not something that happened to the universe. It is something the universe is. The separation between objects is not an obstacle to be overcome. It is the fundamental geometry of reality, encoded in the laws of physics, expanding with the fabric of space-time, and growing more pronounced with every second that passes. And within that geometry, everything that matters to us, every atom, every molecule, every living cell, every thought and feeling and memory exists on a tiny island of matter surrounded on every side by distances that dwarf comprehension. The island is real. The life on it is real. The connections between the people and creatures and ecosystems on the island are real. But the island is small, and the ocean around it is not an ocean of water or air or any substance you could sail across. It is an ocean of vacuum, of absence, of distance measured in light years and megaparsecs and billions of years. And there is no shore on the other side. Astronomy has given us extraordinary gifts. It has shown us the age of the universe. It has revealed the birth and death of stars. It has found planets around other suns and measured the chemical composition of galaxies billions of light years away. It has mapped the cosmic web and detected the faint afterglow of the Big Bang. These are among the greatest achievements of the human mind. But astronomy has also shown us something we did not ask to see. It has shown us that the universe is not built for proximity. It is not built for contact. It is not built around the idea that things should be near each other, reachable by each other, knowable to each other. The universe is built around distance, around separation, around the idea that matter is the exception and emptiness is the rule, at every scale, in every direction, for as far as observation can reach and beyond. The night sky still looks full. It will always look full to human eyes. The points of light are beautiful. The patterns they form are ancient and meaningful to every culture that has ever named them. But the beauty of the night sky is the beauty of a lie. The sky is not showing you what the universe is. It is showing you only the parts that shine. And those parts are so rare, so scattered, so thinly spread across the volume of reality that the spaces between them are not the gaps in the picture. They are the picture. Everything else is decoration. That is what terrifyingly empty means. It does not mean the universe contains nothing. It means the universe is organized so that almost everything meaningful, every star, every planet, every possibility for life is surrounded on all sides by vastness that dwarfs it. The meaningful things are real, but they are exceptions. They are islands in an ocean that has no far shore, and the ocean is not shrinking. It is growing every day, in every direction, at an accelerating rate. The universe gave us light. It gave us matter. It gave us the capacity to wonder, to measure, to reach outward with instruments and imagination. But it placed all of it inside a structure where the dominant feature is not presence. It is distance, not darkness, not danger, distance. And the further we look, the more of it we find. That is what the sky is actually showing you. Not fullness, separation. And it stretches in every direction, at every scale, for as far as reality goes.